Today I will be proving the Fermat's little theorem, which states that any p a prime and a an integer, a to the p minus a is divisible by p. Okay, basically meaning, for example, take p equals 2, and we have that 1 squared minus 1, 0, divisible by 2. 2 squared minus 2, obviously divisible by 2. 3 squared minus 3, which is 6, divisible by 2. 4 squared minus 4, obviously divisible by 2. 5 squared minus 5, it's going to be 20, divisible by 2. P equals 3. So, for example, 2 cubed minus 2 miraculously is 6, and it's divisible by 3. Plug in p equals 5 for 2, and then you get 2 to the 5th, 32 minus 2, which is going to be 30 divisible by 5. So, let's prove it now. So first, let's find floor function, which is going to be the maximum of the integers such that it's less than or equal to x. So what does this do? Well, floor function of 3.1415, it's going to be 3. Basically, it rounds it down. So 1.658, repeat on and on. For example, floor function is going to bring you 1. It just rounds down no matter what. That's how we're going to define floor function. And we're also going to find something called the fractional part, which is going to be x minus floor function x. Basically, what it does is it brings 3.1415 on 2.1415 on, and 1.658 onwards, and it's gonna, not floor function, fractional part, at 2.658 onwards. So it just gets rid of that front one and only gives you the thing after the decimal point. Okay, so now with those in mind, we define Tn of x, a function from 0, 1 to 0, 1, and we define it as Tn of x as being fraction part of nx for x not equal to 1, and x for x equals 1. Okay, so now let's take, for example, T5 of 3. Well, T5 of a half. What's T5 of a half going to be? Well, it's going to be the fractional part of 5 halves, which we all know is going to be 1/2. So that's what it's going to be. Okay, so now let's prove a very important lemma, which states that Tn has n fixed points for n greater than or equal to 2. And proof of this? A fixed point is where Tn brings some number to itself. So Tn of x equals x. So proof of this is because we can rewrite Tn of x in a different form, a piecewise function form. It's going to be nx for x between 0 and 1 over n, because anything in between there, when you multiply it by n, it's going to be less than 1, so the fractional part of something less than 1 is going to be itself. Otherwise, it's going to be nx minus 1 for x between 1 over n and 2 over n, because if you multiply any of these between in this interval by n, you get something between 1 and 2, which will have fractional part minus 1, because the floor function is going to be 1 for those. Continue this down to a general I. So it's going to be this. Okay, so it does n times x minus I for x between I over n and I plus 1 over n. Continue that down until nx minus n plus 1 for x between n minus 1 over n and 1 and 1 for x equals 1. So this is our new definition of the function. And basically what I'm going to do, this little thing right here, is going to be t and I of x. That's how I'm getting to know it. And I'll prove that t and I of x will have a fixed point. So basically what I'm asking is nx minus I equals to x. Now this obviously has a solution. It's going to be x equals I over n minus 1. Now how do I know that this x is going to be on the interval that we want it to? It's going to be, how do I know that this is the case? Well, pretty simply, what you do is you make sure that I on n minus 1 will be a larger number than I on n, right? So that's pretty obvious. Now, the fact that it's less than I plus 1 over n, you just multiply by n minus 1 on the top and the bottom, and then multiply by n here, so you have ni minus multiplying by n minus 1 on the top and bottom, so it's going to be ni minus I, and then plus n minus 1. So those cancel out. Then I get divided by n squared minus n. And then you get n minus I, n minus 1 minus I over n squared minus n, which is going to be greater than 0. Which is going to be greater than 0 for basically any I not equal to n, right? Less than n. So it's going to be greater than 0 for those, and thus this equality holds. Okay. So that's about it. So then I found a fixed point. So that's going to be your ith fixed point. We call that xi. There are n of these tni, tn1, all the way up until tn. N minus 1, tn0, all the way up until t and n minus 1. Each have fixed points. xi, thus n fixed points for tn. And we're good. Oops. Okay, so, haha. Now we've proven that lemma. That is the most important lemma to all of this. You're going to have to memorize it. Because now comes the important part where we actually prove it. Okay, so what we do is we take S to be the set of X. We'll take for TA, okay? So consider TA. Then let's prove another lemma first. Lemma 3. If X a root, a fixed point of Tn. No. That's it's a different lemma. Okay, so Tn of Tm of X is going to be Tn times m of X. Let's do a little proof. Okay, So now we have that. So if x equals 1, it's trivial because both of those map it to 1. So let's do it for x9 equals 1. Then we'll have the floor function of n times the floor function of m times x. Now, by the definition of the floor function, this is going to be n times x minus n times floor function x. But guess what? This right here is an integer, right? N times mx minus n times floor function mx. That's going to be an integer. So if I subtract an integer from this thing I'm taking the fractional part, well, the fractional part of an integer is 0. That's if I'm subtracting off that fractional part. So, for example, 3.1415 minus 2 fractional part is going to give me 1.1415, but it's still going to give me 0.1415 in the end, right? So that does nothing. So we can just get rid of it, and thus it's the floor function of n times m times x, which is the same thing as t n times m of x, okay, by definition. So now that we have these two lemmas, the most important two lemmas, we can now prove the Fermat's little theorem. So we have that. So consider TA. Consider the set of all x such that TA of x equals x. So the fixed points of TA. Okay? Then, by our lemma 3, TA to the p of x equals TA of TA of dot 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 of TA of x for a p there, right? Because you multiply them all together, still going to be equal to x. So x is also a fixed point of TA to the p. So then let us take S equal to the set of all x such that x is a fixed point of a to the p, but it's not a fixed point of a, of TA. So what does this tell us? Well, we know that the number of things in here is going to be a to the p, right? Because that's the number of things in here. But we have to get rid of the a in here. So a to the p minus a. So those are going to be the number of things in here. Then we take something called a orbit. Basically, what you do, x, then TA of x, then TA of TA of x, and you continue that on, okay? But this is going to be equivalent to x, TA of x, TA squared of x, on and on. And because x, an element of the set, it's a fixed point of a to the p. So let's take it up into TA p of x. X an element of s. Okay? So now we have TA to the p of x. Now suppose it was a fixed point of some earlier one, like a to the TA to the c of x is equal to x. Then, because it's also a fixed point of a to the p, we must have it that it's that C must be a multiple of P, which means that C is equal to 1. A contradiction, since we said that TA of x equals x, it's not allowed because that's the definition of a set S. So now we know that most definitely TA to the P of x is the final fixed point in this orbit. So we know also that if TA to the P of x equals x, then CTA to the 2P of x is also equal to x, right? And you can continue that up for all the p's. And basically what it says is that the order of S must be divisible by the order of the elements of x, which are all as we discussed, a to the p, basically meaning, which are all p. The order of them are p, because we apply t to the a, p times, and then we get to our thing. So these have order p, basically meaning order of s, a to the p minus a is divisible by p for p of prime, because it relied on the fact that p was prime to prove it. QED, and we're done. Oh boy. Oh.